Hello, I'm Dr. Reyes Flores. Welcome to this video series where I'll talking about the characteristics of polymers. This first speech will be about the molecular weight. Then, let's go to the issue. A molecule has a group of atoms which have strong bonds among themselves, but relatively weak bonds to adjacent molecules. Examples of small molecules are water, methanol, carbon dioxide, and so on. Polymers contain thousands of millions of atoms into a molecule, which is large. They are also called macromolecules. Polymers are prepared by joining a large number of small molecules called monomers. Polymers can be thought as a big buildings and monomers as the bricks that go into them. Monomers are generally simple organic molecules containing a double bond or a minimum of two active functional groups. The presence of the double bond or active functional groups act as the driving force to add one monomer molecule upon the other repeatedly to make a polymer molecule. This process of transformation of monomer molecules to a polymer molecule is known as polymerization. For example, polyethylene, the prototype monomer molecule, is very reactive because it has a double bond. Under the influence of heat, light, or chemical agents, this bond becomes so activated that the chain reaction of self-addition of ethylene molecules is generated, resulting in the production of a high molecular weight material, almost identical in chemical composition to ethylene, known as polyethylene, the polymer of ethylene. The difference in behavior between ordinary organic compounds and polymeric materials is due mainly to the large size and shape of polymer molecules. Common organic materials such as alcohol, ether, chloroform, sugar, and so on consist of small molecules having molecular weights usually less than 1,000. The molecular weights of polymers, on the other hand, vary from 20 to hundreds of thousands. The name polymer is derived from the Greek poly for many and meros for parts. A polymer molecule consists of a repetition of the unit called a mer. Mers are derived from monomers, which, as we have seen for polyethylene, can link up or polymerize under certain conditions to form the polymer molecule. The number of mers, or more precisely the number of repetitions of the mer in a polymer chain, is called the degree of polymerization. Since the minimal length or size of the molecule is not specified, a relatively small molecule composed only, say, 3 mers might also be called a polymer. However, the term polymer is generally accepted to imply a molecule of large size. Accordingly to the lower molecular weight, products with low dP should preferably be called oligomers to distinguish them from polymers. Often the term high polymer is also used to emphasize that the polymer under consideration is of very high molecular weight. Because of their large molecular size, polymers possess unique chemical and physical properties. These properties begin to appear when the polymer chain is of sufficient length. In other words, when the molecular weight exceeds a threshold value and becomes more prominent as the size of the molecule increases. The dependence of the subtending temperature of polyethylene on the degree of the polymerization is shown in this picture. The dimer of polyethylene is a gas, but oligomers with a dP of 3 or more are liquids, with the liquid viscosity increasing with the chain length. Polyethylenes with dPs of about 30 are grease-like, and those with dPs around 50 are waxes. As the DP's value exceeds 400 or molecular weights exceeds about 10,000, polyethylenes become hard resins with softening points about 100 Celsius. The increase in softening point with change length in high molecular weight range is small. The relationship of such polymer properties as tensile strength, impact strength, and melt viscosity with molecular weight is indicated in this picture. Note that the strength properties increasing rapidly first as the change length increases and then level off, but the melt viscosity continues to increase rapidly. Polymers with very high molecular weights have superior mechanical properties but are difficult to process and fabricate due to their high melt viscosity. The range of molecular weights chosen for commercial polymers represents a compromise between maximum properties and processability. Now, let's go to the molecular weight of polymers. That is the alternatives to obtain molecular weight parameters. In ordinary chemical compounds, such as sucrose, all molecules are the same size and therefore have identical molecular weights. Such compounds are said to be monodisperse. In contrast, most polymers are polydisperse. Thus, a polymer does not contain molecules of the same size and therefore does not have a single molecular weight. In fact, a polymer contains a large number of molecules, some big and some small. Thus, there exists a variation in molecular size and weight known as molecular weight distribution, MWD, in every polymeric system, and this MWD determines a certain extent of the general behavior of the polymers. Since a polymer consists of molecules of different size and weights, it's necessary to calculate an average molecular weight or an average degree of polymerization. The molecular weights commonly used in the characterization of a polydisperse polymer are the number average, weight average, and viscosity average. Consider a sample of a polydisperse polymer of total weight W, in which N is the total number of moles, and I is the number of moles of species I. In other words, the molecules of the same size. Lowercase n and I is the mole fraction of species I. Double I is the weight of species I. Lowercase w and I is the weight fraction of species I. Mi is the molecular weight of species I. Xi is the degree of the polymerization of species I. Then we could define the number average molecular weight Mn as follows. From the definition of molecular weight as the weight of sample per mole, we obtain that Mn is the sum of the multiplication of the molar fraction species Ni by the molecular weight of the species Mi. Well, dividing Mn by the mere weight Mo, we obtain a number average degree of the polymerization, dPn, where dPn is defined by this formulation. The quality Mn is obtained by N-group analysis or by measuring a colligative property such as elevation of boiling point, depression of freezing point, or osmotic pressure. For weight average molecular weight, MW, the molecular weight of each species is weighted by the mole fraction of that species. Similarly, in the computation of weighted average weight molecular weight, the molecular weight of each species is weighted by the weight fraction of that species. Therefore, we have the following formulation for MW. MW is the sum of the multiplication of each weight species by the molecular weight of this species divided by the sum of the weight of the species, as we can see. The weight average degree of polymerization dPW is obtained by dividing MW by the mole weight, as we can see in the formulation. Well, MW can be determined by measuring light scattering of dilute polymer solution. MW is always higher than Mn. Thus, for a polymer sample containing 15 mol% and a species of molecular weight 10,000 and 50 mol% of a species of molecular weight 20,000, the equation 1 and equation 5 gave us that Mn is 15,000 and Mw is 70,000. Viscosity average molecular weight Mv. The viscosity average molecular weight is defined by this equation. For A equal to 1, Mv equal Mw, and for A equal minus 1, Mv equal to Mn. Thus, Mv falls between Mw and Mn, and for many polymers it is 10 to 20 below Mw. Mv is calculated from intrinsic viscosity eta by the empirical equation, where K and alpha are constants. Eta is derived from viscosity measurements by extrapolation to zero concentration. In correlating polymer properties, which depend more on the number of the molecules in the sample than on the size of the molecules, Mn is more useful parameter than Mw or Mv. Conversely, for correlating polymer properties, which are more sensitive to the size of the polymer molecules, Mw or Mv is more useful. Because it is easy to determine, melt index often is used instead of molecular weight in routine characterization of polymers. It is defined as the mass rate of polymer flow through and specific capillarity under controlled conditions of temperature and pressure. The index can often be related empirically to some average molecular weight depending on the specific polymer. A lower melt index indicates a higher molecular weight and vice versa. Well, finally, I'll talk about polydispersity index, the ratio of molecular average molecular weight to number average molecular weight is called the dispersion or polydispersity index A. It is a measure of the weight of the molecular weight distribution curve, as we can see, and is used as such for characterization purposes. Normally, A is between 1.5 to 2.5, but it might range to 15 or greater. For a monodisperse system, in other words, for pure chemicals, A is just 1. There is usually a molecular size for which a given polymer property will be optimum for particular application. So, a polymer sample containing the greatest number of molecules of that size will have the optimum property. Same sample with the same average molecular weight may possess different molecular weight distribution. Information regarding molecular weight distribution is necessary for a proper choice of polymer for optimum performance. A variety of refraction techniques, such as fractional precipitation, precipitation chromatography, and Herpermetion chromatography, or GPC, based on properties such as solubility and permeability, which vary with molecular weight, may be used for separating polymers of narrow size ranges. Well, the next video I will talk about the polymerization processes by chain polymerization, steep polymerization, supramolecular polymerization, and copolymerization. Don't lose it. Even if you are a postgraduate student in polymer chemistry, the next video will be interesting for you.